In this exercise, I would like for us to look at the intersection of two planes, the plane x plus 2y plus 3z equals 4, and 4x plus 6y plus 7z equals 8. So the first thing we're going to do is sketch a picture of these planes, or at least we'll give a diagram for what it looks like when two planes intersect. Then we will describe their line of intersection, and we will wrap up this exercise by finding their angle of intersection. Okay, so first a little art lesson. Let's just quickly go through the best way, in my opinion, to draw two planes which intersect. So what I'm going to do is draw an X that's kind of tall, so like a wide X or a tall X. I'm going to do a tall X, okay, like that. Then what I'm going to do is do like 5 parallel lines off to the left, your left. So we'll do 1, 2, 3, 4, 5. I might change that lower one. Okay, then it's like we're looking at this intersection from the side. So here we see, like this is the line of intersection. Here's one plane, here's the other. And take shape. Then I'm going to connect this corner down to the line of intersection. I'm going to pass behind the other plane, so we'll do dot, 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 like that. And then let's see, I need to go dot, 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 like that. Okay, so those are our two intersecting planes. It's just a representative diagram. They don't have to naturally actually look like the two planes that we have if you put them into some sort of graphing software. What we would first like to figure out is this line of intersection. Whoops. I did fine with my drawing of two planes, but then when I had to draw a straight line, messed up. Okay. All right, so we will give a vector description of this line of intersection. What do we need to have a line? So actually, let me take a moment to pause in case your diagram didn't go so well and you want to start over, and then just think, what pieces of information do we need to have in order to describe a line? All right, to describe a line in space, we need a point and a sense of direction. So on our diagram, let's just imagine that the point we're going to find is this one. And then our sense of direction tells us how to move away from that point to trace out the line. So if my sense of direction points me that way, I can stretch it, or I could negate it and stretch it the other way. And overall, that's going to trace out the entire line. So we just need a point and a sense of direction. Let's actually find that sense of direction first. So I will label it on this diagram as a vector that points us along the line of intersection. And let's call this vector V, like so. To find V, I want to recognize that V lives on both planes. So as I've sketched this vector in space, I've placed it both on the first plane and the second one, which means that it is perpendicular to the vectors which are perpendicular to both planes. So let's add that to our diagram. For this first plane, I'll draw vector n1. So that's like a vector which is orthogonal to this plane. And then for the second plane, diagram's getting a little busy at the top. Let me put it down here. Vector n2 will be perpendicular to this plane. Okay, so V lives on this first plane, which makes it perpendicular to n1, but it also lives on the second plane, which makes it perpendicular to n2. So we want a vector which is perpendicular to both n1 and n2. There's a very systematic way to find such a vector, and that's with the cross product. Okay, so we will find V by crossing n1 and n2. I will write out the cross product as something that looks like a 3 by 3 determinant. So I write ijk along the top, and then we will have the vector n1 will be the coordinates 1, 2, 3 from our first plane. So 1x, 2y, 3z. And then the coordinates of vector n2 will be 4, 6, 7. So you read those coordinates right off of the coefficients for the general forms for those planes. Okay, let's cross these. Let's see, for the first coordinate, we'll have 2 times 7 minus 3 times 6, that's 14 minus 18, negative 4. Then for the second coordinate, we'll do 3 times 4 minus 1 times 7, so that's 12 minus 7, which is 5. And then for the third coordinate, we'll have 1 times 6 minus 2 times 4, that's negative 2. Okay, so let's go ahead and write that. Sorry. The vector v we will use as negative 4, 5, negative 2. I said we will use this vector because this is not the only direction vector that would work. Another vector that would work would be 4, negative 5, 2. If this is v, the vector I just described points the other way. Another vector that would work is negative 8, 10, negative 4. That would be twice as long, right? So any nice scalar multiple of v is also a vector that could serve as the direction vector for this line. But this one will work. So we just need one good direction vector that does indeed point us along the line. All right, let's take a moment to check our work here with cross product. It's always good just to run through it twice to make sure that we didn't have a sign error. And then I will come back and we will figure out how to find this point P so that we can write down the vector description for this line. All right, to find a point which lives on this line of intersection, we just need to find one triple of values for x, y, and z, which makes both plane equations true. So we want to find some triple in three-dimensional space so that 1 times the x coordinate plus 2 times the y coordinate plus 3 times the z coordinate is 4. And also 4 times the x coordinate plus 6 times the y coordinate plus 7 times the z coordinate is 8. This is a system of 2 equations for 2 unknowns. We call this an underdetermined system. It doesn't have a unique solution. So we only have 2 equations, but we have 3 variables. That means there are infinitely many solutions to this pair of equations, which makes sense because there are infinitely many points along this line. So any of the infinitely many points on this line will satisfy both equations at the same time. Sometimes students think this is harder to solve than if I gave them a set of 2 equations for 2 unknowns or 3 equations for 3 unknowns where there might be just one unique solution. Because you have to take it a sort of first step on your own. So you have some freedom here for what to do. What I'm going to do is say, let's see if there's a coordinate on this line of intersection for which the z coordinate is 0. So let me go ahead and start to fill in the information for this point. Okay, so that point's going to have x, y, z coordinates that we're going to work out. And what I want to imagine is that that z coordinate is 0. So I'm going to set z to be 0. And the reason why I'm doing that is because if z is 0, I can just get rid of these from my equations, leaving me with a system of 2 equations for 2 unknowns, which we're going to solve using traditional techniques. So let's just suppose z is 0. If for some reason that had left us with a pair of equations for which there was no solution, that would mean that no point on this line had z equals 0, so we could just make a different choice. Okay, but this is a good one. In particular, what I'm going to do now is elimination. So let me work to the right and write a little bit smaller so that we can fit this on the screen. I'm going to take everything here, z is 0, I'm not going to rewrite this part. I'm going to double it to 2x plus 4y equals 8. And the reason why I'm going to do that is I'm going to take everything we're left with here and cut it in half so that we can cancel out the x coordinates. So this is elimination. You could eliminate differently or you could use substitution as well. At this point, it's not really a calculus problem, it's an algebra problem. So this is 2x plus 3y equals 4. Now I have x coordinates matching, which means if I subtract the second equation from the first one, we'll have 2x minus 2x is 0. 4y minus 3y is great. That's just plain old y. Whoops. And on the right-hand side, we have 8 minus 4, telling us that with this z coordinate of 0, we should fill in a y-coordinate of 4. Now all we have to do is figure out the remaining missing x-coordinate. For that, I'm going to revert all the way back to this original equation here and say that x is 4 minus 2 times the y-coordinate. That's 4 minus 8 is negative 4. So that this is negative 4. All right, let's take another moment here to pause. And what you can do is, if you want to, zero out the y-coordinate instead, zero out the x-coordinate instead, and see if you can repeat this kind of process. Or you could say, suppose z equals 1. Try to find a point that has a z-coordinate of 1. You'll end up again with a system of 2 equations for 2 unknowns. There are so many different ways that you could proceed with this problem because, again, there are infinitely many points on this line. So there are infinitely many ways to satisfy both of these equations at the same time. I recommend doing this if you're not totally confident with this process. If you're like, I'm with you, just go ahead and let's write down the line of intersection before we start talking about the angle. If you wanted a little bit more practice with finding points on the line and you took my advice and tried to find a few other points, if you're wondering if you did it correctly, all you have to do is take the triple you found and plug them in for x, y, and z in our 2 plane equations. If you have 2 true statements at the end, then you've done it correctly. So negative 4 plus 2 times 4 plus 3 times 0 is 4. That satisfies the first plane equation, and similarly, this triple will satisfy the second. Okay, so that's how you can check yourself. All right, we have everything we need now to write down the description for this line of intersection. What we're going to say, I'll call it a function r of t. It's a parametric function. It's going to be this point. So I'll write down the position vector for this point, negative 4, 4, 0, plus the parameter t times the direction vector for the line that we chose. So negative 4, 5, negative 2. Right. I'll say a little bit more and put this in a slightly different organization in just a moment, but I want to point out that this point, this information here, could look different for somebody else's line description. If they came up with a different point, which was also on the line, this could be different. And also this direction vector could also be different. It could be 4, negative 5, 2. Typically, it's easier to identify that you have parallel direction vectors because they should be multiples of each other if they're both correct. This could be really hard to determine just by inspection. So it's possible for 2 people to solve this problem correctly and write down the same line, but to have it look different. This could look different, that could look different. Okay. The other remark I make before I write down kind of coordinate description for this line is that the process I talked about, where I said that v works for the line, but also so would negative v, so would twice v, that's like choosing different values for this parameter t. Okay. So if this, let's say the origin is down here and the coordinates negative 4, 4, 0, sorry, this position vector points us to that point, and then we add to it t equals 1 times our direction vector v, that sends us here on the line. If I wanted to get here, it could be like that plus negative 1 times v. If I wanted to get here, it would be that plus twice v. So this t is what sends us along the line. Okay, probably saying a little bit too much, so let me just wrap up by saying what the coordinates are. Sometimes you want to write it not as one kind of concise parametric description, but you might want to say something like the x-coordinate is negative 4 minus 4t. The y-coordinate is 4 plus 5t. And the z-coordinate is 0 minus 2t. This set of equations would also trace out the line for different values of t. Okay, let's take a break and then I will come back and find the angle of intersection. So what we'll be looking for is that angle right there. The intersection of 2 planes gives you 2 possible angles. So if I make a tall X with my hands like we have on the board, notice I have 2 pairs of angles. I have the top and bottom, and then I also have the left and right. So in this diagram, if my intersection looked like this, I have acute angles above and below and obtuse angles to the left and right. If my planes intersected like this, I would have obtuse angles above and below and acute angles to the left and right. It's just like with two intersecting lines. When you have two intersecting planes or two intersecting lines and you're asked to give the angle of intersection, the convention is typically we want the smaller of the two, so that would be an angle between 0 and 90 degrees. Okay, so we'll go through the process of finding this angle. The methodology we use, I believe, will always return the acute angle. I might have to take a moment to think about that in a second, but if for some reason we ended up with an angle that was like 120 degrees, we would just take its supplement. We would say, oh, it's 120 degrees, subtract that from 180 and get 60. So typically, if you're asked to give the angle of intersection, you want to give the smallest angle, which is opened up. All right, let's say a couple things that are true about this angle, which I'm going to call theta. All right, so that is our angle between these two planes. You find the angle between two planes by looking at the angle opened up by their orthogonal vectors. It's either exactly this angle or it's this other one. Either one will allow us to get to the final answer of theta. If you want a quick demonstration of why that's the case, let's imagine that we draw this plane intersection from the side. So it's like I want to point this line of intersection right at my eye so that the planes look like lines. So we'll draw a two-dimensional diagram. I'm trying to think if I want to also rotate it, but let's not do that. Let's just draw an X. Let's say this is the plane here, and this is the other one. N1 is a 90-degree rotation from plane 1, so that's going to be like this. It's 90 degrees, so I know that this is 90 degrees, and so is this other side. N2 is a 90-degree rotation off of the second plane, so if that's plane 2, it's going to be like this. Doesn't look like a right angle, but imagine that's a right angle. Okay, so we've got right angle here, here, and here. Okay, it's not a perfect diagram. We want to find this angle, which is the same as this one. So this is our angle theta. Notice that this little angle in here is the complement of theta. Likewise, this little angle in here is the complement of theta. So these two angles are the same. I'm not sure I need all of that information, but I just like to start drawing what I can figure out as I see it when I look at these kind of angle configurations. And then this angle in here is actually the complement of this one and also this one. And that's because this is also a right angle here. Let me add that. So this is a right angle and this is a right angle, which means that the complement of this is here, but we already called that theta. Okay. So in this particular version of diagramming two intersecting planes with two orthogonal vectors, the angle opened up by N1 and N2, which probably should have labeled this as N1 and this was N2, was exactly the angle that we are looking for. So if this is the angle we're looking for, we have it here. If my N1 had pointed, say, the other way, let's imagine, and I don't want to spend too much time on this or make this diagram too hard to follow, but let's imagine I went this way, flip it. Then the angle opened up would be this bigger one, okay? But you can still get to the angle that you need by working with this angle here. Okay, I'll leave it there. I think it's pretty clear that we get what we need about the angle of intersection from looking at their two orthogonal vectors. So let's erase this. All right, for that angle theta, let me write down two statements. And these will be in terms of N1 and N2, because now the problem really reduces to an angle between two vectors. The cosine of this angle is N1 dot N2 divided by the length of N1 times the length of N2. Okay. The sine of that angle theta is very similar to this expression, except in here we have a dot product. I'm going to start by writing a cross product. Ooh, that's an N. It's going to be N1 cross into, that's a vector quantity. In fact, it's -4, 5, -2. We need to take that and make it a scalar, compute its length, divide that by the length of n1 times the length of n2, like so. Either formula would work. Let me kind of make a case for both. If I'm told to find the angle between two intersecting objects, I naturally gravitate towards this first one, the cosine version, because it's usually easier and faster to take a dot product than a cross product. So if I hadn't already found the line of intersection, I might just do this. The second one is what I'm actually going to work with, and that is because we already crossed n1 and n2. So we did all that work to find the cross product. Let's keep using it. So we will use the vector -4, 5, -2 inside of the numerator in the second expression. That's one advantage. The other advantage is that this is a non-negative quantity divided by two positive quantities, a product of two positive quantities. This expression here will be greater than or equal to 0. When we take the arcsine of that, it will put us between 0 and 90 degrees. So the default result of this computation will actually be the smaller, this acute angle that we're looking for. With the cosine formula, you could actually get the supplement. So with this, we could actually end up, depending on how n1 and n2 were situated, we could actually end up with the larger of the two angles, in which case we would need to take the supplement. So you can kind of make a case for either one or against either one if you want. I'm going to give you a moment to finish writing this down and the diagram if you were working on it. Then we will come back and we will just wrap up with this second expression. All right, let's wrap this up. For the numerator, we want to take the length of the vector -4, 5, -2. So that's going to be square root 16 plus 25 plus 4. Divide that by the length of n1, which was 1 plus 4 plus 9, times the length of 16 plus 36 plus 49. Which means I'm going to run out of room, so let me just do it right here. This is the square root of 45 divided by the product of two square roots is the square root of their product, so I'll put it in 1. And we will have 14 times 101, which is 1414. If you're impressed with my mental math, okay, I just did that on paper. So, and then actually you could write this as the square root of 45 divided by this 1414. Let's do that. So theta is the arcsine of the square root of 45 over 1414. Be very careful if you're typing this into a calculator to watch your order of operations, okay? Parentheses, that sort of thing, just because if you're typing it in line, like a one-line calculator, you have to make sure that you enter it correctly, and if you do, if you're working in radians, which I was, you get 0.1794 approximately. I knew that I was working in radians. If I didn't, if I had to just make a quick guess, is this answer radians or degrees? Look how very small it is. This is almost 0. In degrees, we're looking for a number between 0 and 90. This being almost 0 means these planes are almost flat against each other. Okay, so that's just a clue that this answer is radians. If you want to multiply it by 180, just right here, you could take this and do 180 degrees divided by pi radians to convert from radians to degrees, and you would get still a pretty small angle, but something that sounds a little bit more like a degree measurement. That would be 10.28 degrees. Okay, so if you have a calculator, do make sure that you actually get these numbers to make sure that you are entering this all in correctly. All right, that wraps up this demonstration. Thank you for your attention.